is broad and it overlaps quite a bit. And so what I want to talk about is something that's going to touch on, I think, a lot of what different people are doing, but sort of give maybe a different perspective on things. So, there's a lot of time this week for those of you who stick with it. Please stop me with questions. I'll try to go slowly, but feel free to make sure you're understanding what's going along. So I want to talk about topics from linear PDE. Really, they're gonna, well, it's PDE is such a huge subject, and there are so many different ways of coming at it. And I was originally trained in microlocal analysis and linear PDE, and then I got very interested in various nonlinear things. And there's sort of a huge ground in between that unfortunately not many people take advantage of techniques from both sides. And I've really tried to sort of build that correspondence between the two, because I think that there are many ideas from nonlinear PDEs that are useful in linear PDE and vice versa. And I want to try to maybe emphasize some of those. But so this is a perspective, not only in linear PDEs, but sort of a fairly novel, maybe modern perspective on things, which is maybe a bit unusual. So let me talk a little bit, let me just give you a brief outline of what I'll be talking about this week. So I'll be talking about, I'm going to start off, and again, this is going to be sort of aimed at a fairly general level. It'll sort of ramp up during the week, but today may be a real review for some of you. So I'll be starting off talking in general about pseudodifferential operators. And so if you know what those are, I will be reminding you, but I'll be presenting sort of them in a new context that may not look so familiar. So I'll be talking about their various properties, definitions, and applications. And so, I mean, why pseudodifferential operators? Well, this is a workshop about non-local operators, and these are kind of the prototypes. These are, very non-local operators, integral operators of a very particular sort, with a very sort of rich set of properties and a very interesting set of applications. So in particular, amongst the applications I'll be talking about are applications to conformal geometry. And this is going to be very closely related to Alice's talks. So I want to give some of the technical background so that she can sort of focus on sort of the geometric and nonlinear aspects, but I want to talk about some of the linear PDE that goes into the necessity for what she's going to be talking about. And then what I want to get to from the title of my story is heading towards fractional Laplacians. So heading towards fractional Laplacians. Now, there are many ways to define fractional Laplacians, as I suspect many of you know, and some of them are very related to conformal geometry, as Alice will be explaining. I'll try to give you some heads up too. But in particular, there's this extension method, which is very closely related to what's called the scattering method. I'll be describing these both. And what I'm sort of aiming for finally is how to adapt these geometric ideas to study the fractional Laplacian on bounded domains. Okay. Now, so that's where I'm sort of heading for at the end of the week. Now, I should say that this is a very much studied topic, and so I think that there are many results. I'll be trying to mention a few of the major contributors, and that what I'll be talking about is a very different perspective on things. So what is the perspective? Well, at the end of the day, both in this conformal geometry application and this extension method, the scattering method, the focus is on what I'll call degenerate elliptic operators. So the whole mid part of the week, I'll be talking about how to define a class of pseudodifferential operators which are related to operators which are degenerate as you come to the boundary of the manifold. By degenerate, they're blowing up or degenerating in some way. And why do we study these? Well, because we're interested in differential operators that have degeneracies. They're very sort of natural classes of these. And to study them, you need degenerate pseudodifferential operators. And there are many different classes of degenerate elliptic operators. There's a very nice coordinate-free definition, which I'll be trying to describe, that sort of generalizes some of the things here. So I'll be talking about degenerate elliptic operators. Now, in particular, I'll be talking about what's called the zero calculus and the iterated edge calculus. So the zero calculus is what's necessary to study some of these problems in conformal geometry that Alice will be talking about in the scattering method. And the iterated edge calculus will be necessary for studying this. So namely, this is for studying degenerate pseudodifferential operators when there's sort of an interface on the boundary. So when you have sort of a sharp interface in data. Okay, so that's a very rough description, and probably you got not very much other than words out of that for some of these things. And I'll try, hopefully, by the end of the week to sort of talk you about all of these things. Okay, am I writing clearly enough? And can you see the bottom of the board? Okay, okay, very good. Okay, so I want to start off with a bit of history. And by history, I mean ancient history, so relatively speaking. So let me start off with something that's very, very classical that you all learned presumably a long time ago, which are Riesz potentials. Okay, and this is to motivate how pseudodifferential operators came about. So a Riesz potential, well, if you're solving Laplacian U equals F in Rn, and let's, for simplicity, just think of F being very reasonable. It can be C infinity 0, or, well, it could be in some LP class or Holder class or so on. But let's suppose it has compact support, just to make life very simple. Okay. Then we know that the solution is given by the Newtonian potential. U is equal to G star of F up to a harmonic function. So this is a solution, and maybe the general solution to this looks like this one plus a harmonic function. Okay, what is G? So G looks like a dimensional constant, which I can never remember, times mod Z to the 2 minus n. Okay, so that's a very well-known formula. Now, what is a Riesz potential? Well, it's a very classical thing that you do in elliptic theory, which is saying if you know something about, if you know that F has a certain degree of differentiability, you'd like to know that U is 2 orders more differentiable. So the way that you'd study that is you'd say, well, suppose I take dzi zj of U. This is equal to d squared g dzi dgj convolved with U, convolved with F, I'm sorry. And this is the Riesz potential. Now, you look at the case where I is not equal to j. And so here's what this thing is. So if I take d squared zi zj of g, so this is going to be this dimensional constant times 2 minus n times delta ij minus zi zj over mod z squared times mod z to the minus n. Okay, so this is an easy calculation. And when I is not equal to j, this term is of course gone. So that's the general formula when I equals j. Okay, so if I want to prove that, for example, F is in L2 implies that U is in, I don't know, it's different. I usually use H2, the solo space with 2 derivatives. There's corresponding statements if you're in LP, that you're in WP2, or if you're in a Holder space, you have 2 derivatives more. So what that really corresponds to is you want to say that this, let me give this a name so I don't have to keep on writing it. Let me call this Rij, for Riesz potential. You want to show that Rij is bounded from L2 to L2, or LP to LP, or C0 alpha to C0 alpha, etc. So it comes down to showing that you have a certain boundedness property of this integral operator. It's a convolution operator, which is a very simple sort of. Okay, so this was the origins of Calderon-Zygmunt theory. So this is in the mid-1950s, and they wrote this very influential and famous series of papers that really started a huge wave of research. And the basic ansatz was the following. You start with an integral kernel, let's call it K, of z and z tilde. Well, let's call it k of z. And it's going to look in the following form. So I'm going to call it omega of z divided by mod z to the n. Okay, so this is, I have something exactly that form here. So this generalizes the Rees potential. And the important part about this omega of z is if I integrate it over Sn minus 1, omega of z equals 0. Okay, now, so why is this important? Well, the point is that 1 over z to the n is not integrable. It just fails to be in L1 locally, right? Simply because of a 1 over r to the n singularity. And so this is what allows you to make a principal value computation. So, you know, when I take k convolved with f of z, which is the integral, so let me just remind you very quickly, this what you do, so you'd have omega of z minus z tilde over mod z minus z tilde to the n times f of z tilde dz tilde. So the point is this is non-convergent precisely because of this 1 over n singularity. And I'm sorry, this omega of z is homogeneous of degree 0. Sorry, omega of lambda z is equal to omega of z. Okay, so we see that exactly there, the zi zj over mod z squared. It's homogeneous of degree 0. Okay, so this doesn't converge, but what you do is you make you note that this is omega of z minus z tilde times f of z tilde minus f of z. Or z minus z tilde. The n z tilde. So I can slip in that extra f of z precisely because of the integral vanishing. Okay, and so I have to rearrange it, but this works out, right? And then you use the fact that if f has some modulus of continuity, I get some vanishing here. And, you know, if it's Holder continuous, this vanishes like z minus z tilde to the alpha, or, you know, all these other properties, but you get a little bit of extra gain here so that this is convergent. Okay, so that's how I use this property here. Okay, so that's sort of this Calderon-Zygmunt theory. Now, it's, you know, wonderful for what it did. They did a lot of things about when omega is very low regularity and, you know, very detailed properties. But at the end of the day, it's not a very flexible theory. So this is very tied to Rn. Why? Well, simply because these are convolution operators. So it's using the additive structure on Rn. It's very tied to Rn. And somehow, well, let me just say it's not very flexible. So it had a lot of deficiencies. Okay, so remember, this is the history section. I said history, right? So what happened next? Well, what happened next was in about 1959, it was the thesis of Bob Seeley. And what he proved was the following, that if I have a diffeomorphism, so let me call it F, as a diffeomorphism from Rn to Rn, let me be sort of non-specific, but let's suppose it's sort of, you know, going to the identity fairly rapidly, or it's compact, you know, it's sort of the identity outside of a compact set or something like this. Well, anytime I have a diffeomorphism and I have an operator, I can conjugate the operator by the diffeomorphism, right? So if I have this operator, so let's call this A of U is equal to K convolved with U, right? So I can take A, F inverse, pull back, and F pull back. So I'll call this A sub F. Okay, so what Seeley did was he computed what this thing was for K being for A coming from a singular integral operator. And, you know, this is kind of a horrible computation. He did many other things in his thesis, but he proved something very interesting, which is that this is equal to another singular integral operator. So that stands for singular integral operator. Plus something better, something more smooth. Okay, what do I mean by something better? Well, by an operator which is given by some sort of integration, but where the kernel is L1 log. Okay, so namely, I get something which has exactly this sort of order of singularity, plus something that's a little bit smoother. Okay, so, you know, it's not a, you know, from a modern perspective, it's not a very hard calculation. This has a very profound significance, which says that there's something coordinated happening underneath it all. So we're trying to move away from being tied to Rn and to gain some flexibility. So the immediate realization, and this was, I mean, by his account, so Singer, when he was teaching me this many years ago, Isidore Singer, he said, you know, immediately he had the realization, he told Seeley, aha, now we can put these on manifolds. And so what this led to is you can define singular integral operators or manifolds. Okay. So you have a class, so if I have a compact manifold, let's suppose n sub n, compact manifold, then, you know, roughly speaking, so here it is, I cover it with coordinate charts, I take an open cover, u sub alpha, this is an open cover of them, and I have sort of local singular integral operators, which are defined in each one of these sets. I sort of use a diffeomorphism to move it back to Rn, take this sort of definition, and then I sort of piece them together. So I won't write it out because it's very messy, but you can do that. Okay? So, so what that means is you have an interesting class of operators and manifolds. Now, what the application that Singer had in mind, well, it was just a couple of years before the famous Atiyah-Singer index theorem, but this was kind of an instrumental realization. And this has turned out to be an extraordinarily useful tool in geometry. Okay, well, continuing the history lesson. Note to the organizers, these erasers are a bit dicey. Exercise. Okay, so what happened next? Well, so people realized that this integral definition was complicated to work with. And so the early 1960s, there was sort of a sequence of papers that were extraordinarily influential and sort of carried this in a new direction. So by Vermander, Kohn and Nierenberg, there were several other papers, but maybe these were the early main contributors to. Ah, thank you. So.
I don't know if it's better or not. It's the same, but
no,
it's
no,
new.
Looks good. Looks new. Let's see what happens. Let me try. That's perfect. Okay, there we go. Thank you very much. Okay, very good. Okay, so what they introduced was sort of a different way, well, let's say a completely different way of capturing operators of this type. So now let me start afresh from a very different point of view, which is the following. So suppose I have a differential operator, so let's call it L. So this is going to be a differential operator. For the moment, it's just going to be on Rn. Okay, so here alpha is a multi-index. And so there's a convention that dzj is 1 over I times d by dzj. This is how you know you're talking to a linear PD person, because they put that 1 over I there. Okay? Okay, so this is a differential operator. Now I should say right away that I'm going to be talking, for the most part, with operators with smooth coefficients, right? So many of you may think that's an extraordinarily strong limitation. And of course it is. It allows you to answer certain questions about operators with smooth coefficients sort of in a very detailed way, but you're not, at the end of the day, completely limited to operators with smooth coefficients. So for example, all these techniques, what they'll do for you is they'll allow you to prove certain estimates that are stable under perturbations. So, you know, there are things that you cannot do with this technique, but there are a lot of things that you can do that don't strictly fall under this rubric immediately. So don't feel like you're completely mapped to smooth coefficients. Okay, so the observation is the following, that especially when L is constant coefficient, but in general, you can represent L using the Fourier transform. Okay, so what I want to do is I want to write U of Z is equal to 2 pi to the minus n, and we'll go e to the I of Z dot zeta, U hat of zeta d zeta. Okay, the standard Fourier transform. And let me immediately make the convention that 2 pi is equal to 1, just because, you know, I'll screw up otherwise. Okay, so we'll forget that factor. Here's the inverse Fourier transform. And if I apply L to U, okay, well, so here's exactly where this factor of 1 over I comes in. If I take dzj applied to e to the I z dot zeta, this is going to bring down exactly, so if I take dzj, brings down a factor of I times zeta j. So this is zeta j times e to the I z dot zeta. So what that means is that this thing is going to equal e to the I z dot zeta times the following expression. Some mod alpha is less than or equal to m. By the way, this mod alpha means alpha 1 plus dot 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 plus alpha n. So this is an operator of order m at most. Okay, and then I'm going to have a alpha of z times zeta to the alpha. You add zeta to zeta. Okay, so it's converted this differential expression into a multiplication operator. And this is a little bit complicated because it's a polynomial in zeta with coefficients depending on z. Okay, so suppose I want to invert L. Okay, well, let's take a really simple case first. So very simple case first. Where L is equal to minus the Laplacian plus 1. This is equal to the sum of the dzj squares plus 1. This expression then, so this, by the way, is called the symbol of L, the total symbol of L. And I'll be defining that in sort of greater generality. For the moment, just say that's the thing you get when you apply this under the Fourier transform. So the symbol of L, in this case, is equal to mod zeta squared plus 1. And this has the virtue of being very invertible. It's a polynomial, and it's very invertible. So if I want to define L inverse, right, it's going to be given by this expression. So L inverse of U has to be given by the following expression, e to the I z dot zeta, 1 over zeta squared plus 1. You have 0. Okay, so I mean, that's sort of the secret of the Fourier transform. It takes differentiation into multiplication, and so inversion of this differential operator should correspond to division. Okay, so it's a well-known classical idea. Okay, so this works very easily simply because this is such a simple operator. So the whole philosophy of pseudodifferential operators is how do I generalize this to when you have a variable coefficient problem? Okay, and it's a bit of a drama, but it's not so bad. There's a little bit of horrible calculations you have to do, but at the end of the day, it all comes out fine. So I'll try to describe what those are. But my aim, remember, I'm sort of really aiming for geometry, is to have a really coordinate-free definition of this. So I'm going to be throwing up all sorts of horrible Fourier integral expressions, oscillatory integral expressions, which look horrible if you don't like this sort of thing. But there's a very nice and clean coordinate varying definition, which I'll be describing in 15 minutes. Okay, so this works fine. And notice that this L inverse, so for example, L inverse is bounded on L2. Right? Why is it? Well, simply because this is a bounded operator. This is a bounded multiplication operator. So if U is an L2, and U hat is an L2 by DOCTORAL, I multiply by something bounded, stays an L2, and I think inverse Fourier transform is still an L2. In fact, it's even better if you think a little bit more. This is bounded from L2 to H2. You have to know what H2 is, but we'll get to that soon enough. So in fact, this is a very nice definition. So the question is, how do you do the same thing here? And if, of course, you can in general, what makes this work is the fact that the sigma bell is invertible. So this algebraic thing you get at the other end is invertible. Okay, any questions about where I'm at? I hope I'm going at a reasonable pace, not too slow, not too fast. Okay, nobody's asleep yet, it's a good sign. Or if you are, it's jet lag. Okay, so here we have this general representation of an L, and so the point is that I want to generalize this definition. So let me start off with sort of a definition. I'm interested in operators A, and well, let me just say right now these are operators a priori from C infinity 0 to D primed. So these are distributions in Rn. Okay, and I'll generalize this, or I'll explain this much more carefully. And these are going to be defined in the following way. AU of Z is going to be defined by, and now I want to, first of all, expand out this Fourier transform definition here. So I'm going to write this in the following way. E to the I Z minus Z tilde dot zeta, A of Z, Z tilde, zeta, U of Z tilde, dZ tilde, dZ. Okay, so this looks like a mouthful. But so first of all, this e to the minus I Z tilde dot zeta, that's just the U hat of zeta there, right? So that's, I've incorporated the U hat of zeta, I've written it out as part of the integral. Then I multiply by something here. This is called a symbol. And then I take the inverse Fourier transform. Okay, so this is different from what I've written there, only in the fact that I've allowed the symbol to also depend on Z tilde. So that's an allowable generalization. Okay, so what I'd like to describe are what are the properties I'd like of this symbol in order for this to behave nicely, to have good properties. Okay.
So in the simple case like this,
Yeah. So in the simple case of the Laplacian, the symbol is 1 plus mod zeta squared. The A is independent of Z and Z tilde because it's a constant coefficient operator. That's exactly right. Good question. Okay, so what properties do we need of zeta, of A? What properties of A are reasonable to expect? Okay, well, of course, as you can imagine, mathematics being what it is, people have found all sorts of softenings of these basic properties. So I'll tell you sort of the original kind of classical definition, and then, you know, I'll say that there are many generalizations of this. Okay, so here's one version of the classical definition. This is motivated by the following fact. In this case, this A is a polynomial in zeta. So it's smooth in Z and it's a polynomial in zeta. Okay, polynomials have the property that they grow at a polynomial rate. Okay, and the other thing is that when I differentiate them, they get better. Okay, so I want to encapsulate those two properties. So what I want to claim is that, well, so let me write out a little bit more carefully. For all compact sets, this is on Rn. So I'm keeping this just as living in Rn for the moment, but it goes on to manifolds very shortly. For all compact sets of K and Rn, there exists, and let's say multi-indices alpha and beta, the multi-indices. There exists a constant C sub k alpha and beta such that the supremum for Z and K and zeta and Rn of dz alpha d zeta beta of A, and excuse me, I've allowed symbols that depend on Z and Z tilde. So maybe I should alpha 1 and no, you see alpha and alpha hat. I don't know. Sorry, dz tilde of alpha hat, d zeta beta of A, Z and Z tilde zeta. Okay, so I differentiate as many times as I want in Z and Z tilde and in zeta, and what happens? Well, the expectation is nothing changes in the estimate when Z and Z tilde. I can differentiate as much as I want in Z and Z tilde. In zeta, what I'm going to get is, this is ck alpha hat beta. I'm going to get 1 plus mod zeta to some order m minus mod beta. Okay, so what I'm saying is that when beta is equal to 0, this grows or decays like mod zeta to the m as I go to infinity. So it's just like a polynomial. And every time I differentiate it, it gets 1 order better. But unlike a polynomial, it doesn't stop when you get to order 0. So it can be differentiating order -1, -2, -3, and so on. Yeah?
Excuse me, in this case, you're telling us about the general case. Are you still talking about the simple case of the Laplacian?
No, this is completely general. Because in the Laplacian case, we'll see how that it plays out in just a second. This is obvious. So now I'm giving you a general definition. Yeah, so indeed, it's a good idea. Let's sort of try this out. So with the Laplacian, the symbol of this minus Laplacian plus 1 is equal to mod zeta squared plus 1. And it's sort of obvious that it satisfies these properties because it's a polynomial. Okay. What about this inverse operator? So what about if I have sigma of minus Laplacian plus 1 inverse? This is 1 over zeta squared plus 1. Okay, why does this satisfy this? So this is a easy but very basic computation. If I take d zeta j of 1 over mod zeta squared plus 1, this is equal to 2 zeta j over mod zeta squared plus 1 squared. Okay, and this is bounded by constant times 1 plus mod zeta squared. So this is minus 4 plus 1 is minus 3. So this is decaying order minus 2. I differentiate once, it decays like order minus 3. Okay, and I continue. So this is kind of a basic property, just the quotient form. Okay, so these things generalize polynomials and their inverses when they exist. So this is the reason for this definition. There's a subclass of these which are very useful and again are even closer to polynomials. So these are called general symbols. Here's a class of things which are called classical symbols. And this is an A, so these things are called, this is called the symbol of order M. So S, so that, S is vertical. Okay, for any M, M can even be a, well, let's say a real number. For any real number M, I can do this. Okay, classical symbols, well, what they require is A of z, z tilde, and zeta has an asymptotic expansion. So let me call this J goes from 0 to infinity of AJ of z, z tilde, and zeta, where these a sub j's are an Sm minus j. So they decay faster and faster. Okay, and the squiggle here is what's called an asymptotic sum, and I'll tell you the exact definition once. I'll be using this many, many times. But it's exactly the sense in which a Taylor series represents a smooth function. It's not convergent necessarily, but it gives you an approximation just like Taylor series do for smooth functions.
Can I ask?
Please.
Is there supposed to be a square on that zeta on the high upward second from the left?
Here?
No, it's only go left on the
Here.
second. Yeah. Is there supposed to be a square on that zeta?
No, so in fact, then I would want an M over 2.
Oh, I see. Okay.
Yeah. So in fact, there's a notation which is kind of very useful, and which I forget to use sometimes, so let me just recall it in case I use it by accident. Which is the following.
M is the leading order of the symbol.
M is the leading order of the symbol. That's right. So here's this notation, which I often use. This bracket zeta is 1 plus mod zeta squared to 1/2. Okay, so this has the advantage that it grows exactly like mod zeta to the order 1, but it's smooth and non-vanishing. Okay, so that's just a nice notation to use. Okay, so where are we? I was trying to tell you what the squiggle means. Okay, so we have A is a symbol of order M. A is asymptotic to this A sub j. J goes from 0 to infinity. And so what do I mean by this? Well, suppose I take any partial sum and subtract it off from A. So I take J goes from 0 to n minus 1 of this thing. Okay, what do I want it to be? I want it to be as good as the next term. What is the next term? Well, this is like A sub n, which is supposed to be an Sm minus n. So this is exactly what the squiggle means. Oops, sorry, AJ. Okay, so if I take A minus any finite sum, so I'm not doing anything infinite here, right? Then I get something of order 1, as good as sort of the very next emitted term of the series. Okay, so this is what a classical symbol is. And again, this is exactly what Taylor series are to smooth functions. Now, there's a very useful lemma here, which I'll state, and it's going to come up in many different circumstances here. So I'll just mention it once and then refer to it many times again, which is called Borel's lemma. Right? And in fact, this is, I know, this was proved for C infinity functions, you know, some version. And this was the old Borel, the oldest Borel, right? Which says, given any sequence, A sub j, which are symbols of order m minus j, there exists an A, which is an SM, such that A is asymptotic to the sum. So this says, the minute I produce the sequence of symbols that are increasingly better, right, then I can find an asymptotic sum. So it's not convergent, but it has this property here. And this is the generalization, and essentially exactly the same proof once you transport over the language, of the following statement. Take any sequence of real numbers that you want. There's a smooth function for which those are Taylor coefficients in the origin. So that was the original Borel's one, I think. I never looked at it. Okay, so we have this class of symbols of order m for any m. And I've talked about general operators here. So finally, the definition, which I complete there, so this is my definition, is that the class of pseudodifferential operators of order m is equal to the set of A's, which are of the form A of u is equal to the sum e to the I z minus z tilde, dot zeta, A of z z tilde and zeta, u z tilde d z tilde d zeta, where A is a symbol of order m. Okay, so this is what a pseudodifferential operator is. Now, this looks horrible, right? Everybody agree? It's pretty bad. I'll give you a much nicer way of thinking what these are. And you want to think of these things as kind of a coordinate representation. It's just like if you have a nice coordinate invariant definition on a manifold of some geometric thing, it looks great. Then you write out the Christoffel symbols, it looks horrible, right? This is the same principle. So this is like just a local coordinate definition of a pseudodifferential operator. Okay, so I've given you a class of operators. The motivation was, well, I gave you two motivations. One is that it seems to generalize, well, I talked about this very special constant coefficient case. I talked about differential operators giving you, did it disappear? I don't know where it went. Differential operators giving you symbols where the symbols were polynomials in zeta, right?
What are the domains of this Z hat?
I'm being very vague about this. Yeah. So the important thing is that zeta is global. Zeta lives on all of Rn. Okay, but the z and z tilde are somehow local, they're defined in an open. So this can be defined on an open set. Okay. So yeah, you have to fuss around a little bit with just, what are the properties, but let's not stand on principle here. Okay, so there's this class. Now the question is, and these also generalize singular integral operators. Why is that? Well, let me just remind you of a basic fact. In fact, I'll tell you a basic fact about Fourier transforms, which we're going to be using many times hence, which is, suppose I have, so let me call this a function w of z. This is a distribution on Rn. In fact, let me say specifically a Schwarz prime distribution on Rn. So remember, this means a tempered distribution, so it's dual to the space of rapidly decreasing smooth functions. Okay, and I want w to be homogeneous of some order. And I want w to be smooth on Rn minus 0. Okay. So I'm taking what's called a homogeneous distribution. For simplicity, it's smooth away from the origin, and it's homogeneous. And remember, for distributions, what does homogeneity mean? I have to interpret this weakly. So this really means, I won't write it out, but just as a reminder, if I take w, so the distributional pairing of w with some test function phi is supposed to be, w of z, phi of z dz. Though if w is a general distribution, this may not make sense, right? So this is only sort of suggestive. So this w sub lambda, right? Well, if I were to have w of lambda z, phi of z dz, let's change variables. So I write this as w of, let's say, z bar, phi of z bar over lambda, dz bar, and let's see, so z bar is equal to lambda z, so dz is equal to lambda to the minus n dz bar. Okay, so this is what the definition of w of lambda z is, distribution. So what this actually says is that this thing is supposed to equal lambda to the a times the integral of w times v. Well, this computation actually now makes clear the following thing. Well, no, it doesn't quite make clear, but one does a little exercise and gets the following fact. That if I have a distribution which is homogeneous of order A, then its Fourier transform is also homogeneous, but of dual order. Okay, so then the fact is that given these assumptions, W hat, which is defined, I mean, W is a Schwarzschild distribution, so the Fourier transform as O is defined, is homogeneous of order minus n minus a. Okay, so it's an easy computation just from playing around with duality in this. So I'll leave that as an exercise. And it's also C infinity in Rn minus 0. Okay. Okay, so remember I have these singular integral operators, things of the form omega of z over mod z to the n. This is homogeneous of order minus n. Okay. What happens to its, so if this is W, what is W hat? Well, it's homogeneous, it's whatever it is, it's homogeneous of order 0. Now, there's a little subtlety hidden in here, which is only for the aficionados, which is, remember, I had this sort of extra assumption here that omega integrated to 0 around the sphere, so it allowed the principal value to be taken place. That's necessary in order for this thing to actually be homogeneous of order minus n as a distribution. If this didn't integrate to 0, then you'd get sort of an extra term, it would be a little bit funny, and what you would find is that W hat was not quite of order 0, it actually grows logarithmically. So if this thing didn't integrate to 0, this thing would have a logarithmic growth. Now, how does this come down to a symbol? So maybe I'll call this. So remember I have this operator, the singular integral operators. A view is, well, sort of in this notation, W convolved with U. What is this as a pseudodifferential operator? Well, this is equal to the inverse Fourier transform of W hat of zeta, U hat of zeta, d zeta. So there's my symbol. There's my symbol. It's a symbol of order 0. Okay. Well, there's one small part I haven't checked here. So I said that this is homogeneous of order 0. You actually need Euler's formula. So Euler's formula tells you that if you have something which is actually homogeneous, even as a distribution, it's C infinity in Rn minus 0, then I differentiate it, it gets better. Every time I take a d zeta j of this, it gets one order better. So it really is a symbol in the sense I've defined it above. Okay, so in other words, singular integral operators are just pseudodifferential operators of order 0. Okay. Okay, so that's sort of the long introduction to what pseudodifferential operators are. Now I'm going to tell you a little bit about their properties, and then we're going to get to why people bothered with all this. So they're profoundly useful, and I'll try to give you some indication of some of the uses. Okay, so what are some of the main properties? Okay, so maybe the first one I'm going to describe is what's going to immediately allow me to put this on manifolds. Namely, that if I have a pseudodifferential operator of some order, and this is, let's say, on some open set U, and I have a diffeomorphism from U to, let's say, V to U. These are between two open sets in Rn. So I have a pseudodifferential operator on U. I have some other open set which is diffeomorphic to this U. Then if I take, oh God, so which way is it going to go? So if I take A composed with F pullback. No, F inverse pullback. I don't know. Exercise to figure out what I did wrong. Okay, so it's one or the other, right? So I conjugate by pulling back. So namely, I take a function here, I pull it back to here, apply the pseudodifferential operator, and then pull it back to V. So this is clearly an operator on things on V, right? Start with something on V, pull it back to U, apply this formula on U, and then pull it back to V. Okay? The claim is that this is a pseudodifferential operator on V. Okay, now why is this sort of non-obvious? Well, so remember, here's this definition, e to the I, z minus z tilde dot zeta, a of z tilde zeta, u z tilde z tilde d zeta. Well, I have to tell you one other thing about these oscillatory integrals. So why is this?
Capital F is a differential.
Yeah, capital F is a diffio. I'm sorry. Yeah. Okay. Very good. So why is this still a pseudodifferential operator? Well, really, what I'm doing is I'm putting an f of w minus f of w tilde here. Right. So I have something where I have nonlinear things to the exponent, and what I have to do is I expand them into Taylor series and then blah blah blah. You do something or another. Right. But at the end of the day, you convert it to something with the same form of the new w coordinates. Okay. So it's an unpleasant computation, but it's not very deep. Okay. So I forget to tell you one thing, which is if I have a general A, which is a symbol of order m, what is this supposed to even mean? Right? So this is called an oscillatory integral, and I haven't defined it for you yet. I've written it down as a formal expression, but I haven't even defined it yet in general. Okay, well, let's think. So first of all, if U is in C infinity 0 or Schwartz, this is fine if I'm on all of Rn, but if I'm in an open set, I need to do something like this. So if U is smooth, compact, and supported, I take the Fourier transform in Z tilde, and I get something rapidly decaying and smooth. Okay, even if this Z tilde there's a dependence in Z tilde and this symbol here, it's still, that's still, I have something compactly supported, so it's still smooth. And, Fourier transform, the function of zeta I get when I take the Z tilde integral is rapidly decreasing. This thing grows at most polynomially. That doesn't beat out the rapid decay. So I have a rapidly decaying thing in zeta, and the integral makes sense. Okay, so in fact, then I'm going to get that this A of U is smooth. Simply because I'm going to have an integral of something rapidly decaying in zeta, and I can differentiate, every time I differentiate in Z, it brings down polynomials in zeta. It never destroys the convergence, so I have something which is smooth. Okay. So that's when U is in C infinity 0. What do I do more generally? Right? And so the problem is that this is growing at some polynomial rate. This is not a convergent double integral. So this makes sense as an iterated integral, but not a double integral. Okay, so what I'm going to do is the following kind of weird trick, which is, let's see, how do I want to say this? Yeah, so, okay, so suppose that I want to make sense of this thing, and I want to use the fact that U is, let me see, I always forget, you have like 3 basic operations, and they all involve integration by parts. Let me try one of them, see if it works. I can never remember which works, right? So I use the following observation. If I take e to the I z minus e tilde dot zeta, yeah, well, suppose I do that. Well, let me just show you one of the basic tricks, and in some variant of this works. So if I take zj minus zj tilde applied to this thing, right? So suppose I'm in some region where this is non-zero, and I take a dzj of this thing. This is going to be e to the I z minus z tilde. Okay, so it's just the fact that if at least I'm in a region where this thing is non-zero, if I take d zeta j of this thing, it hits this guy, it brings down the zj minus zj tilde up to a factor of I, and it gives me the same thing back. Okay, so what does that mean? It means that if I take this, I take this expression and the exponential I replace by, okay, so now let me tell you how I want to use this. Okay, so how I want to use this is the following. So if I have this integral, I can just replace this by d zeta to the alpha of, let me write this as sort of formally as 1 over z minus z tilde to the alpha, e to the I z dot z minus z tilde dot zeta, times a of z z tilde beta u z tilde u z tilde zeta. Right? So all I've done is I've taken this exponential and replaced it by the same expression. And then what I want to do is I want to formally write this as, well, this is the same as 1 over z minus z tilde to the alpha e to the I z minus z tilde dot zeta, and then times d zeta to the alpha times minus 1 to the mod alpha of a times u of z tilde d z tilde d z. Okay, now I've said something slightly wrong because I have the z minus z tilde, and you have to worry a little bit about this, so I'll maybe correct that next time. I just can't think in front of the classroom, right? But the point is here, this is better. This is faster decaying. So if I have a symbol of order m, I can do this for any alpha I want. So what I do is I do it for some very large alpha. I equate this to this thing, just formally, right? This is convergent if I make alpha very big, because this is decaying fast enough to be a convergent double integral, right? And so I take this as a definition. So what do I have to check that this is a reasonable definition? Well, just the fact that it doesn't matter which alpha I took. So suppose I took some alpha that did this, and this is convergent, or I took a different beta, which does this, and this is also convergent. Then all I have to show is that the expression with alpha and the expression with beta are the same. But these are all in the convergent regime, so I can integrate by parts from one to the other. So namely, I make a choice, but it doesn't matter which choice I make. Okay, so I hope that that's not too muddy. Okay, so I've formally taken this expression, replaced it by this. So this is a regularization of this integral. And the claim is that how many times I integrate by parts is an immaterial choice. It doesn't matter. Okay, so that's how I define oscillatory integrals. Okay, so moving right along. So any questions? Yeah.
With this trick, we can define it on which class?
Excuse me?
With this trick, we can define the pseudodifferential operators on.
Well, so for example, when U is an L2 or LP, or so the point is that you need. So what do you need here? So you need the integral in z tilde to be good. Well, if A is compactly supported in z tilde, then that's not going to be a problem. So as long as U is sort of locally L1, we're good. And then A can be a symbol of any order. So the point is, if U is locally in L1, right, and A is a symbol of any order, then this is a well-defined double integral.
We cannot reach Schwarz distribution.
Schwarz distributions? How do you mean?
Like with similar operators, under certain condition, you can define.
Well, so I mean, I'm sort of being, again, a bit sloppy about domains, but indeed, depending on assumptions on A. So for example, I've just defined A saying that on any compact set, it's good. But suppose I say that the estimates in Z and Z tilde are uniform in Z and Z tilde. Then it's fine to let U be a Schwarz function, for example, things like that. So there are many modifications of this which are very easy. And the main, but this is sort of the main step of how you sort of regularize the integral. Good. Any other questions? Okay, so what are the things that we'd like to do with these, or what are the main properties? So let's start off with main properties. And the first thing I stated with was that there's a coordinate variance here. And so let me just tell you a fact, which is that we can define, using this diffeomorphism invariance, the class of pseudodifferential operators of any order on a, let's say, a compact manifold. So I can always define pseudodifferential operators in compact manifolds. Okay? Namely, I just take this definition when I chain them together with diffeomorphisms, I get things of the same type. Given any pseudodifferential operator, there exists a symbol, and let me call it sigma sub m of A. And this is a function of z and zeta. And what is it? So the important thing is that you have to do some more calculations. You have to sort of see what happens here. This is a smooth function. This is a smooth function, and it's going to live on the cotangent bundle of M. And so in fact, here's M, here's a point Z, there's all the fibers of the cotangent bundle. So for a given Z, zeta is somewhere up here in the fiber. So the important thing is that zeta is naturally transforms like a cotangent variable. And if you think about it, this is just the chain rule. You know, so if I take what is d by dzj, how does it transform? It transforms like a covector. Okay? So the point is this is naturally a smooth function. This is a bundle, coordinate invariant, which has a linear structure in each fiber. And so when I talk about these polynomial estimates, this polynomial growth or decay on fibers of T star M, that's a completely well-defined thing. If I'm in a compact manifold, I don't have to worry about uniformity. I choose some norm on each fiber, and I'm going to have a well-defined notion of polynomial growth on the fibers. Okay, so I get this operation. Now I wrote the sigma sub m, and the point is that it's not completely defined, or well-defined, simply because, well, I get a lot of junk terms when I change variables. Okay, so in fact, here's the. So I'm going to do some algebra now. I'm going to write down a short exact sequence. So here's, in fact, a crucial fact. If I take psi sub m minus 1 to psi sub m to psi sub m plus 1, psi sub m modulo psi sub m minus 1. So all I'm doing here is this is a short exact sequence. All this means is that any operator of order m minus 1 is an operator of order m just by default. And this is the quotient algebra. I haven't told you the algebraic properties. I'll tell you that in a second. I have Sm minus 1, I have S sub m, and I have S sub m modulo S sub m minus 1. So these are exact sequences. And what's well-defined is this map. So this is a completely coordinate invariant thing. Namely, if I take a symbol modulo junk terms of order m minus 1, I get a pseudodifferential operator, but it's only well-defined up to something of order m minus 1. Okay? So in other words, I'm saying if I take a symbol of order m, there is a mapping, this is called the quantization mapping, which takes a symbol of order m to a pseudodifferential operator of order m. Namely, I just write down these oscillatory integrals in local coordinates. I've made a lot of choices in doing it. How does it depend on choices? Well, only by junk terms that are of order 1 less. Okay. So this is sort of the well-defined thing, and that's important here. Another property is that if I take a pseudodifferential operator of order m, let me sort of just represent it in this way, and compose it with a pseudodifferential operator of order m primed, this is a pseudodifferential operator of order m plus m primed. Okay, that's not a shock, that's kind of what you'd like for these things to be true, and that's true for differential operators. If I take a differential operator of order m and m prime, they compose to something of order that's the sum of the two orders. But it's not so obvious when they do this with pseudodifferential operators. So there's a real theorem here. Okay. This corresponds on the symbol level to something that's much more obvious. If I take a symbol of order m times a symbol of order m primed, that's a symbol of order m plus m primed. Okay, so the point, and this is kind of explains the word symbol. I take these very non-commutative objects, these operators that, you know, they're kind of very big infinite dimensional operators, and I replace them by symbols, which are much simpler abelian objects. So that's kind of the idea, is I take something that's very non-commutative and replace it by something that's much more commutative. Okay, and this is a well-defined operation, but only in this sense here, in this quotient algebra. Okay, so I have this composition formula mirroring sort of a much easier fact that when I multiply symbols of two different orders, I get a symbol of the combined order. Okay, so that's one of these. So the main properties are diffeomorphism invariance, the existence of a principal symbol, this exact sequence in this commutative diagram, this algebra property, and maybe the last one, which I'll put over here, we're not going to use it too much, which is that if I take the adjoint of an operator with respect to some measure, and I take its symbol, it is, not very shockingly, the adjoint of the symbol. Okay, so these are all properties. So this is my foray into algebra. So there are many places to read about this. I'm not telling you details, and let me give you a couple of things. Now, as I say, we're planning to be moving to a coordinate-free definition, but I want to give you a couple of applications. Well, let me give you Now I'm going to talk about some applications, and then I'll talk about the coordinate redefinition. So let me give you sort of 2 or 3 main applications. So the first one is one of the raison d'etre of the whole thing, which is the elliptic parametrics construction. Okay, so this says the following. Suppose I have an A, which is a pseudodifferential operator of order M. This is defined on some manifold. This manifold, for the moment, doesn't need to be closed. It can be open. It can be open set in Rn. And suppose that the following is true. If I take the principal symbol, suppose that it's bounded from below by 1 plus mod zeta to the m for mod zeta bigger than some constant. Okay, so what happens near zeta equals 0 doesn't really matter. All I care about is what happens when zeta is getting bigger and bigger. So remember, here we are in the cotangent bundle, and I excise some neighborhood of the 0 set, and all I'm asking for is estimates outside that neighborhood of the 0 set. Okay, so this is called ellipticity. And it's exactly the notion of ellipticity that you all know and love.
Additional solution.
Excuse me?
That's an additional solution.
It's a, what did you say?
Did you say you assume that?
I'm assuming that.
Yeah.
So assume. That's not automatic. So the claim is, so then, and this is a theorem, if A is elliptic, then there exists a pseudodifferential operator B of order minus m, such that A composed with B is equal to the identity minus R1, B composed with A is identity minus R2, and here R1 and R2 are pseudodifferential operators of order minus infinity. So I'll give you an indication how to prove it, but the basic idea is the following. If A is elliptic, so I have this lower estimate, then 1 over this thing makes sense, at least when zeta is big. Okay, so this thing is invertible outside of a neighborhood of the 0 section, and so the symbol of B is supposed to be just 1 over this thing. That's kind of morally the proof, then you have to do some more crap. Okay? So, and what do symbols of order minus infinity mean? Well, remember, if I have a symbol, e to the I, z minus e tilde dot zeta, times some r of z tilde zeta, u z tilde d z tilde d zeta. If this is of order minus infinity, what does that mean? It means I take u, take its Fourier transform, multiply by something rapidly decaying, and take the inverse Fourier transform. I get something smooth no matter what I put in. So no matter what u is, the output is smooth. That's why it's called a smoothing operator. Okay. So what I've done here is I've said that if I have an elliptic operator, then I've inverted it up to smoothing operators. Okay, and you should think of this as being morally invertible, or invertible in a functional analytic sense. So it may not actually be invertible, but it's pretty darn close. Okay. Now the whole beauty of this proof is it's completely algebraic. It just solving, and this is kind of the whole secret of microlocal analysis. You're just solving things in Taylor series. Okay. So what I want to do is the following. So I take this A, and I want to find a B. So this is the parametrics. So this is called parametrics. So parametrics is just an inverse up to low order error terms. Okay, so I want to find B. So what I'm going to do is I'm first going to try to find an operator of order minus m. That's going to solve identity, and let me call this Q1, where Q1 is a symbol of order minus 1. So the identity is an operator of order 0. Excuse me, that's a pseudodifferential operator. Okay, the identity is an operator of order 0. I want to find it modulo something a little bit better. How do I do this? Well, I'm just going to take the principal symbol mapping. I'm going to get sigma sub m of A times sigma minus m of B minus m is equal to, well, the product of the principal symbols, this is m and minus m, I get something of order 0. That's going to be the principal symbol of the identity, which is 1, minus the principal symbol of Q1. If Q1 is the pseudodifferential operator of order minus 1, its 0th order symbol is 0. So what that means is all I'm trying to do is invert this symbol. Okay? And I can do it by ellipticity. Now I can't quite do it because, there may be all sorts of zeros in here. Sigma sub m. But what I do is the following stupid thing. I take sigma sub minus m of B minus m, and I'm going to take it to be 1 over sigma sub m of A, and then I multiply by some cutoff function, chi of zeta, which is 1 when zeta is big and 0 when zeta is small. So that's it. That's this B minus m. Now, what I've done is I've defined the symbol of B minus m. I go back and look at my diagram, which I fortunately didn't erase yet. I have a symbol of order minus m. I can lift it to a pseudodifferential operator of order minus m. It's not quite well defined. It's well defined modulo things of one low order. Okay, so let me keep that board up there and let's do this over here. Oops. I don't know which is the good one now. I think this one. So what I've actually done, right? So I've solved this equation exactly at the level of symbols, which means that if I lift it to the level of operators, the remainder term has to be of order minus 1. That's exactly the null space of that short exact sequence. Right? So what that means is I've solved this equation. I've solved this up to an operator of order 1. Okay? Now I'm going to do something slightly crafty. I'm going to say, well, I'm going to try to solve B minus m plus B minus m minus 1 is equal to identity plus Q2, where Q2 is in psi minus 2. So I try to solve it 1 order better. Yeah. Sure. That's a good idea. Let me take 5 minutes. Thank you. Yeah, we're near the end, but yeah, I'm sorry. So let's take a couple of minutes and breathe. Thanks, Paul.
Oh, sorry. It's a 90-minute talk.
It's a 90-minute talk. Oh, okay. Never mind. You got me for a little while longer. I have to finish the proof, right? Well, let's take 2 minutes and everybody breathe, okay? So, no, it's fine. It's good to just relax for a second, and then we'll I'll drink some water. So. Yeah.
Okay, so in this theorem, you said like if A is elliptic, then there is this B, which is a differential operator of order minus n. So in that case, it's like you have A elliptic, but in this case, it's a different case or is it this theorem?
No, so this is this theorem. So I'm proving this theorem.
Okay.
And so all I said is that there's some operator of order minus m with a remainder term of order minus infinity. And through step 1, I've found an operator with a remainder term of order minus 1. Okay? The next step is I'm going to find a remainder of order, I'm going to find a better approximate inverse with a remainder term of order minus 2.
You start doing this recursively.
And I do this recursively. That's 100% right.
Sorry, where did Q1 come from?
Well, Q1 came from the fact that if I took this thing, the 0th order symbol is 0. So that means that the 0th order symbol of 0 is 0, which means that it's a symbol of order minus 1, which means it came from an operator of order minus 1. That's the point. Any other questions? Yeah.
Is this the same as saying you can find the Green's function modulo error, which is
Better.
found as by some order?
Yeah, I mean, that's basically all I'm doing. So I found something where the Green's function is, the error term is a little bit better, right, than the identity. It's slightly better than just being bounded. And then what I'm going to do is correct it so that the error term becomes extremely bounded, becomes a smoothing operator. But see, at this stage, I've already kind of won. I found something which is an inverse modulo something a little bit better. That's exactly right.
So is that the same, you can find, you can control the error of the Green's function near the pole. You can control the contribution from a given neighborhood away from the pole.
That's different. We'll get to that, but that's not quite the same. It's not quite the same. We're sort of. This is a very general construction. It applies in infinitely many cases. So I'll give you other examples, but okay. Okay, so well, taking our break. So how do I find a slightly better remainder term here? So what I want to do is I want to take A composed with B minus M minus the identity minus Q1, right? And what I know about that is that the symbol of order, if I take this thing, the symbol of order 0 of this is equal to 0, which means that it's equal to an operator of order Q1. So if I take A composed with, now I try to find a B minus M minus 1. So this is going to tell me that A, B minus M is equal to the identity minus Q1. If I try to find this thing is equal to Q1, so this is what I'd like to solve. I'd like to kill off this error term. This is a symbol of order M minus 1. So the product is of order -1. That's an operator of -1. Right? So if I take sigma sub M of A, sigma sub minus M minus 1 of B minus M minus 1, this is the mystery guy. I still don't know what that is equal to sigma minus 1 of Q1. I do know what that is because I found it at the previous stage. Okay, how do I solve this? Well, I have to do exactly the same thing. I have to divide by sigma sub M of A. So that's the nice thing. I never have to deal with the low order part of the symbol of A. I'm always dealing with the principal symbol of A. I only ever need this ellipticity assumption. Okay, so this tells me that B minus M minus 1 is the quantization of this chi of zeta times sigma minus 1 of B of Q1 divided by sigma sub M of A. So that's how I find this operator. Okay, so I'm just solving things in the, so I convert this operator theoretic statement into an algebraic statement. I solve the algebra, that's easy. And then I quantize the symbol to get back an operator. And that solves the original operator theoretic equation. So the upshot of what I've done is I've solved modulo order 2 now, and I can keep on going. So let me just write out very quickly what happens. So namely, I now find an operator B minus M, B minus M minus 1. I can find operators of any order, which make the error terms better and better and better. And I choose this Borel sum. So remember, I said I'm just going to immediately sum these guys up. It's non-convergent, but I can still make sense of that as an operator. And the whole point is that now A composed of B is equal to the identity plus something in order psi minus. Okay. So I've just reduced the operator statement to an algebra statement.
You sum at the level of operators, not symbols?
You can sum at the level of symbols and then quantize that. Yeah.
Okay, so this Q is the same map you know for the exact sequences. Watch it. Is there a name for it?
The Q?
Yeah.
Just the remainder term at that stage. No need to do a specific name, but it's just whatever the remainder term is, and you know it's an operator of order -1. Okay. So again, as Alice just pointed out, this is a very general construction. You know, all I need is sort of this algebra properties, differential operators, and you know the symbol map. That's what I need. And so that will come back to haunt us in more geometric stories, or help us, whatever. So the other thing you need is what is the boundedness on function spaces. So before I sort of say what this elliptic parametrics construction buys for you, let me just point out the following fact. So here's a couple of things you can prove. One is that if you have an operator of order M, then A is bounded between Sobolev spaces, HS plus M to HS. Okay. I'm not going to tell you the proofs of these things. That would maybe take us a little bit extra time, and I want to get on to other things. A is bounded from ck alpha to ck plus m alpha. Okay, it's bounded from ws plus mp to wsp. There are sort of very general properties. There's a nice property on Bessel spaces. So you can talk about A being bounded on general Bessel spaces, and these are all special cases of Bessel spaces. So you have to prove each of these things a little bit differently. This follows almost from DOCTORAL. This is kind of very closely related to DOCTORAL, but you have to do a symbol calculus construction. This guy, you use the Paley-Littlewood decomposition to do. And there are many ways to do this, but Paley-Littlewood is a good way to do that as well. Okay, so what do I get from all of this? Okay, so here's the big payoff, which you know how to prove by many other methods, but it's the following: that if there's a theorem, is that if A is a pseudodifferential operator of order m on a manifold m. Now, let me put in a little bit of twist. I can put in vector bundles without problem because these symbols can be matrices instead of just scalar functions, right? All I need is in local trivializations, I get matrix value things, right? So let me not make any drama about that. So there's a, I can put in a bundle there. Okay, if this is elliptic, and M is compact, right, then A is squared. Okay, so it's morally invertible. It's invertible to compact there. There's a finite dimensional kernel, finite dimensional kernel. Okay. So I'm not going to say too much more about how things extend to symbols, to bundles. It just, if everything's matrix valued, the only difference, what's the definition of ellipticity? It just says the inverse of the matrix is a polynomial bit. You do the obvious things at every stage. Okay, so what's the proof of this? Well, we have an inverse, so there exists a parametrics. So an inverse up to operators, so it equals an inverse modulo compact errors. And this is a standard characterization of Fredholm operators. Okay, why is the smoothing operator compact? Well, if I map into smooth functions, and by the way, I should say Fredholm on what? Well, on L2, or any of these other spaces if you like, any solo space or whatever. So there exists a parametrics which is an inverse modulo compact errors. Why is the error compact? Well, it maps into smooth things, and smooth functions include into any one of these spaces compactly on a compact manifold. That's just relative. Okay, so I have a parametrics, and that means that I get the right there. Closely related is elliptic regularity. Maybe I'll state this, I'll write this on the board up here. So elliptic regularity gives you a precise statement about how singularities are related for if you have AU equals F. Okay, so elliptic regularity says that if A is elliptic, and A of U is in HS, then U is in HS plus M. With corresponding statements for Holder spaces and LP spaces. Okay. How do I prove this? Well, I use the parametrics in the opposite order. So what I have here is I apply this to A of U, so I'm going to have B of A of U. So I'm going to have U is equal to B of A of U plus R of U. Okay. This guy is an HS, so this whole thing is an HS plus M. Because B is of order minus M, and I have this boundedness from, well, if A is of order minus M, then it maps S minus M to S, or S to S plus M. It smooths you out. This guy is smooth. So that means that U is an HS plus M. That's it. That's elliptic regularity. Let me give you a small twist, which is very useful, which is what's called the pseudo-locality property of pseudodifferential operators, but in particular this thing. Suppose that if A of U equals F, and F restricted to some open set is C infinity, well, let's say in HS, then U restricted to that same open set is HS plus M. Okay, so here's my whole manifold. Horrible things are happening away from U. So here's an open set. Away from U, I don't care. It's some terrible distribution. But in here, I happen to know that F is pretty nice. It's in some HS space. Then in that same open set, U is HS plus M. And of course, A is elliptic. Okay. What's the proof? Well, I'm going to do a small twist to what I did, which is I take F, which is a distribution on a manifold and has whatever properties, and I take a cutoff function. So chi is in C infinity 0 of U. I take any cutoff function. So then chi times F is an HS. Right? Just by definition, I've localized it to the set F by multiplying by a cutoff function. I have to prove that Sobolev spaces are localizable in this sense, and that's a standard lemma about Sobolev spaces. Okay, so chi could be 1 on a slightly smaller open set, and then it goes off to 0 very rapidly. And now I want to compute, suppose I want to compute what is A of chi U. Okay, well, it's equal to chi of AU plus the commutator, A composed with chi of U. Okay, what can I say about chi of AU? A of U is F, so this is chi times F. So that's something that we know all about. Okay, so if I didn't have this term here, what I'd have is that chi times F is an HS, so that says chi times U is an HS plus M. That's the elliptic regularity. But I have this bad term I have to worry about. What do I do with that? Okay, well, once again, this diagram, which I'm now finally going to erase, is what comes to help us. So the commutator between two operators is a little bit better than you expect. So if I take A composed with chi minus chi composed with A, that's what this thing is. This is a symbol of order 0. This is an operator of order 0, just multiplication by a smooth function. That's a nice bounded thing. It's an operator of order 0. That's an operator of order M. If I take S sub M of this thing, that's going to be S sub M of A, S sub 0 of chi, minus S sub 0 of chi, S sub M of A. And remember, symbols are abelian. Symbols are commutative. So this vanishes. So what that tells me is that A times chi minus chi times A is actually is an operator of order minus M minus 1. So it's a little bit better than A. Okay, so here's the kind of thing that you need to do to complete this proof. I know that U is somewhere. It's a distribution, so it's in some Sobolev space. So let's suppose it is in HT. So T is maybe extremely negative. I don't know what it is, but T could be very negative, but that's globally on the manifold. What does this equation tell me? This guy is an HS plus M. Actually, that's an HS, I'm sorry. And this guy, well, this is an HT, and then I differentiate it. Is that A of chi U is an HS plus, so that's the HS part. This guy is an HT, but M minus 1 orders less, so plus HT plus M minus 1. A was elliptic, so that tells me that chi of U is it's M orders better than this. So it's in HS plus M plus HT plus 1. Now, if T plus 1 is much smaller than HS plus M, then what I've done is I've improved my information. U is in HT, right? So this guy is in HT plus 1. I know something a little bit better. Okay? And I keep on doing this. I keep on iterating this until I get to the case where HS plus M is the smaller of the exponents. So I just iterate this finitely many times, so I'm going to conclude at the end of the day that chi means in HS plus n. Okay, so that's elliptic regularity. Okay, so I'm going to go on for several minutes, and then I'll stop. Where did this, so this was proved in the early 1960s by Hermander, Kohn, and Ehrenberg, several very important papers, and what this directly led to, there was a, yeah. Yeah.
What is a good place to read these generals?
Okay, so there's, okay, I'll tell you two good sources. So there's yeah, there are two very good sources. I meant to write that down, so let me do it now. So one good source, and this is all from the sort of classical point of view, this coordinate-heavy point of view. So it's a book by Misha Shubin, and it's called Pseudodifferential Operators in Spectral Theory. And then there's some very nice new lecture notes by Peter Hinz. He's at ETH, and these are called Lectures on Pseudodifferential Operators or something like that. And I'm trying to get him to publish them, but they're great. These are two really good sources that kind of follow this approach, though. Peters is kind of going to be verging on the description, which I'll need to get to, this coordinate variant description.
The second things are new, relatively new.
This is very new. This is within the last 6 months. Very new. Hot off the press. Maybe a year or something like that. But Shubin's book is now 20 years old or something, and it's very detailed, very complete, and he really crosses all the T's and dots the I's and stuff. It's very, very nice. Okay, okay, so where did this lead? So why was Hermander and various people interested in this? Well, really, why was his Singer and Atiyah interested in this? This sort of immediately leads to the Atiyah-Singer index theorem. I mean, immediately with a lot of stuff in between. But the Atiyah-Singer index theorem basically says if I have an operator, let's say mapping C infinity of ME to C infinity of MF, it's an elliptic differential operator. Okay, so it's differential, which means in local coordinates, you don't have to use this funny oscillatory integral description. You can use just straight on derivatives. Okay, then A is Fredholm, as we know, implies that the null space of A is finite. The co-kernel of A is finite, dimensional, which means I can define the index. Okay. I can define the index of A as the dimension of the kernel minus the dimension of the co-kernel. Okay, so this is an integer. And the remarkable thing is that this is very stable. That's why you have any hope of computing it. It's stable in the sense that if I perturb A by compact operators, in fact, if I take any family of Fredholm operators, the index stays locally constant. Okay. So they actually gave a formula for what this index is in terms of, well, the symbol of A. Now, let me just give you a few ideas about why the pseudodifferential calculus is so powerful for this. Right? So I have some general operator I know nothing about, but it's elliptic. Now I want to compute its index. Well, so the idea is I can take A, I pass to its symbol, okay, and I want to start doing stuff with the symbol. I want to deform the symbol, because remember the index stays constant as I vary the operator, as long as I stay within Fredholm operators. Okay, so I want to deform this to something simpler. So I'm going to deform it to some symbol. So I've used A, let me call it A primed, sigma span of A primed. This might be some other operator, and the point is I can deform it to some operator where I might be able to compute the index more simply. Okay, now if I'm stuck with differential operators, if I have to deform polynomials, you know, especially matrix value polynomials, You know, it's a very non-convex problem. So how do I choose a path from one invertible matrix value thing to another invertible matrix value thing? It's very hard to do. But if you're allowing yourself to deform within C infinity functions, it's very easy. It's just homotopy theory. So basically, there's a purely homotopy theoretic characterization. You take any symbol in the same homotopy class, so it stays elliptic. Now that's just a topological condition, and I get to some other operator. So the idea basically, now the other thing I can do is I can get to some operator, let's call it A double prime, which is an operator of order, let's say 1. What I do is I multiply by something invertible of order 1 minus m. So I take some B, which is elliptic, invertible of order m minus, of order 1 minus m. So if I multiply by an invertible operator, it doesn't change the index. So namely, I can take a general nth order differential operator and deform it gradually to a first order elliptic operator using just homotopy theory, and hopefully this comes down to some operator which I can compute. So what they observed, the T and Singer, was that under various conditions, you can do this so that you get a Dirac operator. And then it becomes a very deeply geometric problem. How do you compute the index of Dirac operators? And that was something we solved separately in various different ways. But the whole point was this flexibility. Pseudodifferential operators allowed you to say, take a very general operator and deform it to something really simple. And that's because deforming amongst polynomials is very hard, but deforming amongst smooth functions is very easy. Okay, last statement for today. So there was another application, and this is sort of getting to the heart of what we'll be talking about later this week. In fact, what everybody will be talking about later this week. This was done, I don't know, back in 1965 or so. So this is about 1965, I don't know, somewhere around there. This is Bob Seeley, again. He's a great and very undervalued mathematician with many extraordinary contributions. So what he proved was the following. So let's take a compact Riemannian manifold. So compact Riemannian. I'm giving you essentially a special case of what he did. Out of this, I can find the Laplace-Beltrami operator, Laplacians of G. Okay. This is a differential operator of order 2. And it's elliptic, as we all know. And so the claim is that there exists a family of operators, A sub t. These are pseudodifferential operators of order 2t. These are all elliptic. And they have the following properties. Let's keep this here. So A sub t composed with A sub s is equal to A sub t plus s. A sub 0 is equal to the identity. A sub 1 is equal to the Laplacian. Let's say minus the Laplacian. So namely, A sub t is equal to minus the Laplacian sub g to the power t. So it's the power of the Laplacian. Okay, it's a semigroup, so this is dead on the nose. This is an exact formula, no remainder terms. So we actually defined a family and we identified every one of these powers of the Laplacian as pseudodifferential operators. Okay, and they form the semigroup property. They extend the identity, and A1 is equal to Laplacian. Because Laplacian is order 2. So when t equals 1, I want it to be order 2. So this is a stupid reason. How did he do this? So forgive me, it could take 2 minutes to explain how we did this, because we have all the machinery. So the secret about pseudodifferential operators is you spend an hour and a half developing this machinery, and then you can do 25 things like in 2 lines. So there's a big startup costs. No, A sub t is 2t. Sorry, that's, yeah, there's a slash. And in fact, I can extend this t to be a complex variable. And I may be lying because there may be some poles. This is a meromorphic family, and there may be some poles, I forget. Okay, so how do you do something like this? Well, let me tell you. So here's what the sketch of proof. So the first step is I take this minus Laplacians of G minus lambda. That's an operator, elliptic operator. So the spectrum of Laplacian is some discrete set of numbers, lambda j, r plus. That's here's the spectrum. By the way, this fact also follows very easily from what I've done before. It's invertible modular compact operators as discrete spectrum going to infinity. Okay, then I form the resolvent of lambda, which is minus the Laplacians of G minus lambda inverse. This is called the resolvent family. So this will be something we'll be talking about a lot tomorrow. Okay, this is a meromorphic family of operators. And what are these operators? In psi minus 2. So every one of these guys is a pseudodifferential operator of order minus 2, and it depends meromorphically on lambda. Where does it have poles? Well, precisely where this thing is not invertible. It has finite rank poles at these eigenvalues. Okay, so complex analysis is a very good tool here. So I have a meromorphic family in psi minus 2, and then I'm going to take a contour integral. So I want to define a sub t to be the integral log c to the 2t times, excuse me, I want to take lambda to the 2t times r of lambda and lambda. I'm integrating on some contour where the contour is, looks like that. So it's just the Cauchy integral formula applied to this meromorphic family. Okay. Now, what do you need to make sense of this? Well, first of all, we know that these are all pseudodifferential operators for every lambda. You need to have sort of estimates on how they depend on lambda as lambda goes to infinity, so that I can integrate it. So this is actually a convergent integral when t is negative or something, and then you have to do some tricks for t positive. But so this is something that you can understand as an integral, always. And when I integrate a family of pseudodifferential operators to some order, it stays in pseudodifferential operators of the same order. Well, so this is going to be an operator of order 2t. Okay, and that's the proof. Namely, I've defined this operator a sub t by this formula, and then the fact that it satisfies all of these things is almost, you have to do some basic operations of complex variables, meromorphic functions. It's very simple. So here are the fractional Laplacians defined in general. They're all pseudodifferential operators. This is okay, so I'll stop there.
If t is order 2t minus 2.
No, it's of order 2t. Oh, you mean with this definition?
Yeah.
Probably. So make it 2t plus 2. So whatever it is, it's supposed to be that. Well, no. So because if I take t equals 0, if I take t equals 0, then I'm integrating the resolvent, I get the identity operator.
On your side, look like there's a minus. So
Yeah.
confusing. Your side, your character side.
Oh my. Okay. Oh, you mean there? Yeah. Okay. Yeah. That's size of 2t.
Yeah.
Yeah. But yeah. So this when t equals 0, this is the integral of the resolvent. That's the identity operator. So the orders match up. Any other questions, Paul?
So what happens if you have a sub-elliptic operator?
Yeah. So, I mean, subelliptic means that the principal symbol may not be invertible. At least, okay, there are various classes of subelliptic operators, but subellipticity is a complicated subject, as you know better than anyone, right? But the point is that so here's, for example, something that you might do. Suppose that the principal symbol of A is not bounded below by mod zeta to the m, but is bounded below by mod zeta to some other power. Let's say m prime, where m prime is less than m. Okay, what that means is that if I take 1 over sigma sub m of A, then this is bounded by symbol by mod zeta. This is bounded by mod zeta to the minus m prime. So that's still a good operator. So the point is that there's still, in many cases, and I forget what the limitations are, but you can still make sense of a parametrics construction for subelliptic operators. Now, there's a couple of big differences for some of the subelliptic operators that you know and love, like the Laplacian and various DRV and so on. What you need to do is work with slightly more general symbols. So for example, if I take the heat operator, dt minus Laplacian, what is its symbol? I tau plus mod c squared. If I take the inverse of this, 1 over I tau plus mod c squared, that's not bounded by 1 over tau squared plus mod c squared. Right? And it is bounded by this to the 1/2, but that's a bad estimate. So it sort of is anisotropic. It decays slower in tau than it does in c. So you invent different symbol classes to handle things like that. So there's all sorts of fancy symbol classes that you can use to handle various types of sublimited operators. But there typically are very good parametric constructions, well, for many classes of sublimited operators. Going back, so I mean, Gilcombe was, of course, great developers of this theory. Vermonter had a very important paper on this in the mid-60s and so on.
Any questions? Okay, so let's thank the speaker.
We resume at 4. We have the next 4.
So thinking about we have a complex structure, so we normally talk about differentiation